What's up, guys? Uh, in this video lecture, I would like to talk about the equation of simple harmonic motion. Okay, so I want to um, find out how the position or the velocity or the other quantities, physical quantities, varies with time in simple harmonic motion. Okay, so equation of simple harmonic motion. Okay, so as I've already told you that any motion is considered simple harmonic motion if the acceleration can be expressed as a linear function of minus x. Okay, or we write it like this: a plus omega square x is equal to 0 if the acceleration can be expressed as a linear function of x. Then we say the motion is simple harmonic. So this is the uh, governing equation of SHM. Okay, if we try to write it in differential form, the differential form can be written very easily. Acceleration is nothing but second derivative of x, so d2x upon dt square plus omega square x is equal to 0. So if you are able to form a differential equation in x, okay, which satisfies which is of the form as shown, then you say that the motion is simple harmonic motion. Now just think about it. How do you think the x should vary with time? Just think, if the x suppose varies as a polynomial of time, let us say t to the power n plus t to the power n minus 1, something like this. If you are going to differentiate x twice, d2x by dt square, then the power of t to the power l will come down by 2. Okay, some constant will come here. Similarly, n into n minus 1. Similarly, some constant t to the power n minus 3, and so on and so forth. Okay, now can this equation add up with this equation and become 0? That is simply not possible, because this equation, the power of this equation is greater than the power of this equation. Okay, the sum can never be 0. So it cannot be a polynomial function. It's very simple. If you could just do a little bit of hit and trial, if you're not aware of differential equation, how to solve a differential equation, if I take x as a sinusoidal function, let us say it is a sinusoidal function, some form of sine omega t, a sine omega t. If you differentiate it twice, then in one of the differentiation it will become cosine will become cos, and if you differentiate it again, it will again become sine. And now the linear combination of the acceleration and the position can be equal to 0, because this is basically the same function, only the constants are changing a little bit. Okay, so what does it mean? That this differential equation has a solution which is sinusoidal in nature. Okay, so this differential equation has a solution which is sinusoidal in nature. So the position varies as a sinusoidal wave. So we like to write position as x is equal to a sine omega t plus phi naught. Okay, here the a represents amplitude or maximum displacement from mean position. Maximum displacement from mean position. This omega represents angular frequency. So omega represents angular frequency. T is the time and phi naught is the phase constant. Okay, this is the position. X is the position as a function of time. So all the quantities are self-explanatory except the phi naught. So let me shed some light on phi naught. If you see, if I put t is equal to 0 in the equation, I will get x is equal to a sine phi naught. Okay, so I can say phi naught is nothing but sine inverse x at 0 upon a. Phi naught is nothing but sine inverse x at 0 upon a. So phi naught is giving us the information of the position when the time is 0. So what is the job of phi naught? The phase constant. It tells us the position of particle when t is equal to 0. So in the initial position of the particle at t is equal to 0, where the particle is located, that can be determined by phi naught. Okay, so let me just summarize. X as a function of time t is a sine omega t plus phi naught. Okay, this is the phase constant which gives us the information about the initial position of the particle, and this is the general phase at any given time t. Okay, x is the position and a is the amplitude. So this is the basic idea for the of how the position varies in a simple harmonic motion. We'll try to solve a question in the next lecture. If you want to find the velocity of the particle as a function of time t, then all you need to do is differentiate. So velocity as a function of time t will be nothing but dxt by dt. So this will be a cos omega t plus phi naught into omega using the chain rule. Okay, so this becomes a omega cos omega t plus phi naught. Okay, so velocity as a function of time t is a omega cos omega t plus phi naught. Okay, so we'll start from here. In the next lecture, I'll be telling you how the energy varies in simple harmonic motion, and I'll relate this equation with a spring block system. Okay, thank you.